All right, good morning. My name is Antonio Fortunato and I'm the Deputy Head of the Crew Operations Unit at the European Astronaut Center in Cologne. Today we will discuss the European experience on the International Space Station. We have covered the major European contributions to the ISS program. There are some additional contributions, but those are really the big ticket items. There is one thing that we shouldn't overlook, however, and this is the contribution that Europe gave in terms of experience through its astronauts. I put here on the slides just a summary of all the European missions and the European astronauts who have flown to the ISS since the beginning of the program in 1998. Now, I don't want to go into the details about what each and every mission accomplished. That would be a story of its own. I just want to summarize that up to this point, Europe has flown 22 missions, 22 astronaut missions to the ISS. ESA astronauts have spent a total of almost 1,500 days in space, and they have participated with 12 EVAs. 9 were shuttle-based. They were related to the assembly of the ISS, while 3 were station-based and happened in the last 2 to 3 years. Now, we have discussed the contributions of Europe to the program. We have seen how many missions Europe actually flew to the ISS with its own astronauts. But what does one of these missions typically look like? Well, obviously the missions that were flown for the assembly of the station were very special. They depended heavily on the objective of the mission, on the piece of hardware that needed to be installed and so on. And they were each unique in its own way. On the other end, after the assembly was complete and we started having long duration missions on the ISS, the setup became a little bit more standard. And this is the kind of scenario that we would like to focus on in the next few minutes. Now, to understand how a typical mission of an ESA astronaut on the ISS looks like, we need to first understand how the flight plan works. Now, the space station planning is based on vehicle traffic. The unit of planning is the increment, and the increment is defined as the period of time between 2 subsequent undockings of the Soyuz. Now, this is true right now, where we only have Soyuz able to carry astronauts to and from the ISS. Obviously, it used to be a little bit different when the shuttle was still flying, because we had crew members actually also rotating on the space shuttle, and it will be again different when the commercial vehicles will start ferry astronauts back and forth. But for the moment, we have a very simple, a very neat plan, and the way it normally works is that astronauts fly for the equivalent of 2 increments, which is about 6 months, 160, 170 days in space. And obviously at any point in time, we know when the Soyuz will go up, we know when they will return, and we know then how many flight opportunities are actually available for the program overall in the coming years. Now, how are those flights assigned to specific international partners or to specific astronauts? Well, this depends on how much each partner has actually contributed to the ISS program over the years. Europe has an overall contribution of about 8.4%. So based on this data, we can go ahead and see how many flights Europe has actually assigned, and there is a specific panel that actually decides when those flights will be over the years. 2015 has been a very busy year. We had the mission of Samantha Cristoforetti up to June. Then we had the short duration mission of Andreas Mogensen in September, and in December we will have the launch of Team Peak for another long duration mission. But this is a little bit of the exception. Normally, ESA supports 1 6-month flight per year. This is more or less the average rate which we have seen in the past year since the assembly of the ISS was complete. Each of those missions can be subdivided in 3 main phases. We have the training, the on-orbit stay, and the post-flight. And when we think about a mission, we have to consider all those 3 phases together. We cannot just reduce the mission to the on-orbit phase, to the flight. Now, looking at the relative durations, we understand that actually flying to the ISS, it's a big commitment in terms of time and in terms of effort. Just the training necessary to stay for 6 months on board the space station is 2.5 years. And then after the flight itself, there are at least 6 months of post-flight. So when you put everything together, for every astronaut flying to the ISS, there is a commitment of about 3.5 to 4 years. Now, let's go step by step through those phases. Training is by far the largest element of the mission. The ISS is the result of an international cooperation, so actually training is also performed in different locations. Mostly it is done in Houston, Moscow, Cologne, and Tsukuba. Most of the training, as you can see from the slide, is actually performed in the first 2 locations. So an ESA astronaut normally would spend about 38 weeks, which is 40% of the training plan, at the Johnson Space Center in Houston, learning how the systems of the US segment work, how the payloads of the US segment work, and also training on the integrated emergency scenarios. They would also spend about the same amount of time, 42 weeks, at the Gagarin Cosmonaut Training Center in Star City near Moscow. Now, in Star City, astronauts learn how the Russian segment works, both in terms of systems and payload operations, but most importantly, they learn how the Soyuz vehicle works, how launch, landing, rendezvous, and docking actually are performed, what are the emergency operations, and so on and so forth. Now, this is the biggest part of the training. Just Houston and Moscow account for about 85% of training time. The rest is divided between training at the European Astronaut Center in Germany, where astronauts learn about Columbus, its systems, the ESA science, and in the past they learned about the operations of the ATV. Or in Tsukuba, where at Space Station Integration and Promotion Center, astronauts learn about the Kibo module, its systems, and its payloads. 2.5 years is a long time. There is a lot of traveling back and forth. Finally, time for launch comes, and as mentioned before, launches right now are only performed out of the Baikonur Cosmodrome in Kazakhstan on Soyuz vehicle. How a launch campaign works would be again a topic for a presentation of its own. It's a very interesting time. From a historical perspective, it's very interesting to participate in those launches also because this is the place where human spaceflight in a way was born. The launch pad that is used for the Soyuz to fly to the ISS is actually the same launch pad that was used by Yuri Gagarin during his first flight. It's called Gagarin Start. Launch on Soyuz, the power part of the flight lasts about 9 minutes, and then in a typical scenario there are 6 hours to perform rendezvous to the ISS. This is actually something relatively new. In the past there was the so-called 48 hours rendezvous. The crew was actually living in the Soyuz for 2 days, and this obviously was not a very efficient use of time, and it was also not very comfortable for the astronauts. The Soyuz is a fairly small vehicle, and it is clearly much better to get to the space station as quickly as possible. Now, the Soyuz is an incredible vehicle. It's obviously a fairly old one. It has been updated over the years. The avionics has been changed, and in general, the overall capabilities of the vehicle have been improved. Its first flight was in 1967, and we are still using it right now. And the Soyuz is a very flexible vehicle. It's a very safe vehicle. During its history, has proven time and again that everything can be thrown at this vehicle, and there will be always enough redundancy, enough margin to keep the crew alive and safe. So the crew is trained, has launched, docked to the ISS. Now they have 6 months to spend on the ISS doing what? Well, the ISS is first and foremost a laboratory. It's first and foremost the place where breakthrough science is implemented. And there are really different types of research that are carried out on board. We have mentioned before, Columbus is especially good when it comes to human life science. A lot of interesting experiments have been performed over the years, but there are also experiments in technology. There are technology demonstrators that are flown here. You see in this picture ESA astronaut Paolo Nespoli working on the microgravity science laboratory in the US lab. And this is actually another nice example of how Europe contributed to the ISS program. The MSG was built in Europe and then handed over to NASA for operations. Speaking about human life science experiments, you see here Samantha Cristoforetti during her last mission working on the PPFS, is the portable pulmonary function system, and this is the piece of equipment that was actually used for an experiment called airway monitoring. An experiment targeted at understanding how the respiratory system actually changes in response to microgravity environment. This has been a very interesting experiment to support because of its operational setup. Every astronaut has to perform 2 sessions on airway monitoring, one at ambient pressure, and this is done in the US lab, and another one at reduced pressure at 10.2 psi, and this is performed in the airlock. Now, especially the part performed in the airlock has been extremely interesting and extremely delicate to implement, also to make sure that throughout the experiment crew safety could be guaranteed. Of course, although science is the primary objective for the astronauts, there is still a lot of systems maintenance that needs to be performed. The first module of the ISS was put in space in 1998, and a lot has happened ever since. A lot of hardware has failed, a lot of preventive maintenance has been necessary, and in general there is a sizable amount of time that astronauts spend on systems maintenance. You see here ESA astronaut Andrei Kuipers working in Columbus on inspecting the ventilation system. We had noticed at some point that the performance of our fans was degrading, so we asked Andrei to look at the ventilation system and to try to understand if there was a blockage anywhere. It was a very interesting activity. The inspection was done with the camera that was actually inserted in the ventilation ducts, and it was also interesting because we thought the blockage was in a certain part of the ventilation system, but well, it ended up that it was in a completely different location, and it was actually Andrei to notice where the problem was and to fix the issue himself. And you see here another example of maintenance. This is astronaut Luca Parmitano performing or preparing to perform a degassing of the water loop for the thermal control system of Columbus. Now, robotics is also a very big part of astronauts' life on board. It is important because most of the cargo vehicles flying to the ISS right now rely on the robotic arm to be attached to the space station. At the moment, only the Progress is actually able to rendezvous and dock automatically to the ISS. The HTV, the Dragon capsule, and Orbital, they all need the Canadarm to be grappled and attached to the space station. That's why astronauts train intensively on robotics. They train intensively, especially on tracking and capture those vehicles. And you see here an example of the HTV being attached to the robotic arm and being in the process of getting berthed to the ISS. EVA is also important. Now, there were a lot of EVAs performed during the assembly phase of the station, hundreds of EVAs just to bring all the pieces together and making sure that the cables were attached, that all the equipment was in place. With the completion of the assembly, of course, there wasn't anymore a need for performing so many EVAs. But it is still important to retain this capability because there is a lot of equipment that is actually outside and that can fail. And we need to have the possibility to send astronauts out and do maintenance on this equipment. And we had a few examples in the past years where we had issues with an MBSU, is basically a fancy power box, and with one of the pumps pushing ammonia through the external thermal control system of the station. Actually very complex, very difficult EVAs, but carried out successfully by our astronauts. You see here actually a picture from the last station-based EVA. This is astronaut Alexander Gerst during the EVA and actually looking at the latching end effector, or one of the two latching end effectors of the Canadarm. This is another interesting picture that actually comes from the time where the station was still assembled. The solar panels of the ISS were not brought to space fully extended. They are very large, they are very big, and there was obviously no vehicle that was actually able to carry them to space unfolded. So they were actually flown in the shuttle in a folded configuration, and then there was a very delicate operation after attachment to the ISS to unfold those panels. Those panels are in many ways a marvel of technology, but like every marvel of technology, something can always go wrong, and at some point during the deployment of one of those panels, they got stuck. And when something like that happens, it's not very easy to find a solution. I mean, look at this picture. There was a need to operate and perform activities at the very end of the solar panel. And the only way to do so was to actually connect an astronaut to the tip of the robotic arm and push the robotic arm as far as possible to give the opportunity to the astronauts to check the solar panel and do whatever was needed to actually unstack it. Now, one important point to make here is that we currently don't have the capability to fly in EVA a la George Clooney. We don't have a system that allows the astronauts to be detached completely from the ISS, fly to the place where they need to be, and perform their operation. We have an emergency system that is called the SAFER that can be used, but it has a very limited autonomy and it is only utilized in case of emergency. Most of the time, the crew has to rely on moving through handrails or being attached at the very end of the robotic arm and being carried by the robotic arm wherever it is necessary. One type of activities that shouldn't be underestimated is outreach. We do groundbreaking research on the ISS. We experience incredible types of operations, and we want people to know. We want people to understand the importance of the program, and that's why astronauts spend a fair amount of their time doing in-flight events, talking to school, talking to journalists. And This is actually a very nice picture because it shows the crew in a moment where all the 5 international partners in the ISS program were represented on board. You have ESA astronaut Frank Devin for Europe. He was, by the way, the first European commander of the ISS. You have Bob Thirsk from Canada, Koichi Wakata from Japan. He later became the first Japanese commander of the ISS. For Russia, Roman Romanenko and Gennady Padalka, and from the United States, Mike Barrett and Tim Cobra. Now, 6 months might sound like a long time, but with all those activities and this much going on the ISS, it actually flies very fast. At some point, the time comes to re-enter, and re-entry is, of course, performed on board a Soyuz vehicle. It takes about 3 hours, 3.5 hours from the time the Soyuz detaches from the ISS to the point where it actually re-enters in the steppes of Kazakhstan. Now, you have to understand, astronauts are exposed to microgravity for 6 months. They exercise, they make sure that their body is still fit by the end of the mission, but still, after 6 months of 0G, it is not exactly pleasant and it is not exactly easy to manage the 3 to 4G that are involved in a normal Soyuz re-entry. And those 3 to 4G become actually even more when you have a ballistic re-entry, but this fortunately happens very, very rarely. Also, after getting the G loads from the re-entry itself, the astronauts have to experience an additional shock, which is induced by the soft landing rockets. Now, you see the soft landing rockets firing in the pictures here on the left. And by looking at the picture, you quickly understand that the soft landing rockets actually do not provide a soft landing at all. As one astronaut said, they only turn a fatal crash into a survivable crash. Anyway, they are necessary. They fire at an altitude of about 1 meter from the ground. And after the capsule sets down in the steppes of Kazakhstan, the recovery forces come on helicopters and all-terrain vehicles, and they extract the astronauts and cosmonauts from the capsule. They check that everything is okay, and then in a very efficient and in a very timely way, they wrap up everything, and within an hour and a half, 2 hours from landing, the astronauts are already on their way to the deployment airfield, where they will then board the airplane that will bring them either to Moscow or to Houston in the United States. There is here a very nice picture that was taken in September at the landing of Andreas Mogensen. This is actually Andreas immediately after the opening of the hatch. He was just about to be extracted from the capsule. Post-flight is a period of about 6 months after landing. Obviously, a lot happens during training, a lot happens during the on-orbit permanence of the astronauts, and debriefings are necessary. Engineers need to understand what went well, what didn't go so well. Flight controllers need to have feedback about how to improve operations. So a big part of the post-flight is spending debriefing the different stakeholders about how the mission went and what could be improved, what could be done better in the future. There is also a lot of public relations going on. Astronauts go around and talk about their amazing experience to different people in their countries and around the world. Finally, after about 6 months, the post-flight period and the mission itself come to an end. The astronauts re-enter the core with their normal duties, and they wait for their next assignment.